Now let's look at example 2. It says, suppose we have a small population of student grades. We have a 65, an 87, a 76, a 96, and a 72. So the first two things that I want you to identify are N and mu. Remember, capital N stands for population size, and mu is the population mean. So I'll give everybody a minute to go ahead and calculate those two values. You could even pause to get the mean. So for capital N, our population size, we have 1, 2, 3, 4, 5 data values. For mu, the mean, if I were to add up 65 plus 87 plus 76 plus 96 plus 72 and divide by 5, I would end up with 79.2 for the mean grade of this population. Now, again, not so realistic to have a population of size 5. We're working with a very tiny population in this next example, just so I could illustrate something to you. Obviously, if the population was much larger, we'd have a lot more work to do. So I'm keeping this example small, 5 data values in my population, but not that realistic. But it's enough for me to show you where I'm going next. So now let's list all of the possible samples of size n equals 2 from the above population. And we're going to calculate the mean of each sample and the sampling error for each sample. So I already went ahead and I listed all the possible samples of size n equals 2 for you, just to save a little bit of time. So what I did was I said, okay, if I'm going to go to this population of 5 data values and just randomly close my eyes and pick 2, what are all the possible groups of 2 that I could have chosen? And there's 10 different possibilities, and they're listed here. So for example, one of the samples of size 2 that we could have picked is 65 and 87. Or we could have picked the 65 and the 76. We could have picked the 87 and the 72, and so on and so forth. So there's only 10 different ways that we could select samples of size 2. I just chose 2. We could have done 3. We could have done samples of size 4. It's just I wanted to keep this small. So the smaller the sample size, the smaller this table is going to be for me to show you something. So I said, all right, pick all samples of size 2, and here they are. So we have 10 different samples of size 2 that are possible from this population. Now what I want you to do is I want you to calculate the sample mean X bar for each one of these samples. So I'll do the first one with you. So 65 and 87, what's the mean of that sample? And there's only 2 data values. So add up 65 and 87, divide by 2. You should get 76. So take a moment to pause. And I want you to fill in the rest of the sample mean. So fill in the rest of this column. So get X bar for all the rest of the pairs of size 2. And I'm going to fill them in as well. So I filled in the remaining sample means. You could go ahead and check your answers just to make sure that you got them all correct. So each one we can use as an estimate. So let's suppose randomly we picked the sample of size 65 and 87. We got the sample mean of 76. We could use 76 as an estimate of the population mean. But remember, we know the population mean. It's 79.2. So it's not such a horrible estimate, right? It's kind of off, but not too far off. 65 and 76, if I were to use that sample and calculate the sample mean to estimate the population mean, we'd have a 70.5, which is definitely further away from the mean, not, as good as an estimate. But remember what I said in the last lecture. Anytime we use X bar, the sample mean, as an estimate of the true population mean mu, there's always going to be sampling error, right? There's going to be a difference between the true value of the population mean and the estimate that we're using X bar. So now what I want to do is I want you to calculate the sampling error for each one of these sample means. So I'll do the first one with you. So to get the first sampling error, let me erase this. Remember, sampling error is X bar minus mu. We take the difference between the estimate that we got and the true value. So for my first one, it's going to be 76, and we have to minus the mean of 79.2, and we get negative 3.2. So that would be my sampling error. For the next one, we would have 70.5 minus 79.2, and we would get a greater sampling error. That difference is negative 8.7. So I'm going to have you pause here, and I want you to fill in the rest of the sampling errors. So take the difference between each sample mean and the true population mean and finish filling in that column, and I'll do it also. So take a look and make sure you got all these sampling errors. And if we kind of just scan, we could see that some of the sampling errors are bigger than others, right? So it looks like this is the biggest sampling error right here, this sample, the 87 and the 96. The sample mean is 91.5, which is really far from 79.2, right? That difference is 12.3. But right underneath, it looks like the 87 and the 72 are a pretty good representation, right? Because if we take the sample mean, we get 79.5, which is not too far off from 79.2. There's only a difference or a sampling error of 0.3. So that's how we interpret these sampling errors. So now what I want to do is, let's talk about the sampling distribution of the mean. What is that? Because this is going to be the main idea of the first part of this chapter. So remember probability distributions, which we looked at in chapter 6 and 7. In chapter 6, we talked about discrete probability distributions and binomial probability distributions. And then in chapter 7, we were looking at continuous probability distributions, right? Specifically normal distributions, data values that were normally distributed. So this here that I'm circling, this table in front of you, that's a sampling distribution, which is a probability distribution for the sample means that we listed in example 2. So all these means up here, you see how I listed them again? So here's all my sample means from the above example. I listed them. And then right next to it, because remember, a probability distribution lists all the data values along with their associated probability. So remember in chapter 6, when we were talking about discrete random variables, we had these discrete probability distributions where we would list the values of X, right? And we would put the probabilities, and it had to satisfy certain criteria, right, in order to be a probability distribution. So this is a probability distribution for X, right, a discrete random variable. This is just an example that I made up on the spot. Well, this here, this is also a probability distribution, but now my random variable is X bar. So we have all the different values of X bar listed here, and then the probability of X bar. So if we go back to this list up here, what's the probability that if we were to select one of these samples at random, that the mean is going to be a 76? Well, there's only one sample that has a mean of 76, right? It's this one. So it's 1 out of 10, right? Because there's 10 different sample means here. So that's why I have 1 out of 10 as the probability. And they're all going to be 1 out of 10 because there's only one 70.5, there's only one 80.5, and so on and so forth. So all these X bars are equally likely. They all have a 1 in 10 chance of occurring. And this probability distribution for the sample mean still satisfies the same criteria, right, that we started talking about in chapter 6, where all probabilities, right, have to be between 0 and 1. So same goes for the probability of X bar occurring. And then the sum of all the probabilities in a sampling distribution, right? Remember the sum of all the p of x's has to sum up to 1. But in this case, my random variable is x bar. So the sum of all my p of x bars has to add up to 1. And if we were to add up this column, we're going to get 10 out of 10, which is 1. So this represents a sampling distribution of the mean. So if we were to take all the sample means that are possible from all the different groups of size n, which was 2 in this case, and list all their respective probabilities, that's called a sampling distribution. And you're going to see later on in the chapter why these are important. Like why would we ever have to even discuss the sampling distribution of the mean? So we'll get there. For now, I just want to explain what is a sampling distribution of the mean. So it's just a probability distribution, but now my random variable is x bar. And it's a probability distribution which lists all the sample means from all possible samples of the same sample size selected from the same population, along with the probability associated with each sample mean. So what is the mean of this sampling distribution of the mean? So you see how each one of these values of x bar is equally likely, right? They all have a 1 in 10 chance of occurring. So all we have to do is add up all these data values, add up all the x bars and divide by 10 because there's 10 of them, right? That's going to give us the mean of all the means, essentially. So I want you to take a minute, you can pause, and I want you to sum up all the x bars and divide by 10 and tell me what the mean is. And you should have gotten 79.2. And that's kind of cool, right? Because that should ring a bell. What else was 79.2? Wasn't the mean of the original population equal to 79.2? Right? Remember, we took the mean of those 5 data values and we got 79.2. That's not a coincidence that if we were to take the mean of all the sample means of size n from the same population, we're going to end up with the mean of the population. And that's going to be the mean of all the sample means. Now we have a specific symbol that we use for the mean of all the sample means. So let's talk about notation for the mean of the sampling distribution of the mean. We use this symbol called mu sub x bar, which is this guy right here. It's a mu with a little sub x bar next to it. We can't call it mu, right? Because mu is the mean of a population of x values, but we're not looking at a population of x values. We're looking at a population or a distribution of x bars. So that's why we write mu with a little sub x bar. So it's telling us that this is the mean of all the sample means. So this is the symbol that we use. And we realized that it's equal to mu, which is the mean of the population. And I wanted you to see that. We might as well also talk about notation for the standard deviation of the sampling distribution of the mean as well. So sampling distribution of the mean. So if I were to get the standard deviation for this data set right here, all those sample means, I would use sigma, but with a little sub x bar, very similar to mu sub x bar. So this sigma means standard deviation, and then this little sub x bar means of all the sample means. So that's the notation that we use for the mean and the standard deviation of the sample means. So we'll stop here, and in the next lecture, we'll pick up where we left off, and we'll talk about calculating mu sub x bar and sigma sub x bar and their significance.